Now, in our last lecture we were discussing about the finding the multiple roots for an equation f x is equal to 0. What we were really looking for is a multiple root of f x is equal to 0. We know the definition of multiple root, that if let us say x is equal to xi is a multiple root of multiplicity m. So, let us take this multiplicity also, it is a multiple root of multiplicity m. Then we know that f of xi would be 0, then its derivative is also 0, f prime of xi is equal to 0, and so on up to m minus 1th derivative it is equal to 0, and the mth derivative is not equal to 0. This is the basic definition of the multiple root of multiplicity m. Now, to find this particular root, we shall first of all attempt whether we can use the methods that we have derived for simple roots by some modification or some other criteria, that we can use those methods, so that the not much changes have to be made in the methods that we have. Let us first of all attempt in this particular form. We know that if f of x has got a root x is equal to xi of multiplicity m, then its derivative f prime of x has got the same root x is equal to xi of multiplicity m minus 1. Therefore, we would like to consider a function which is the ratio of these two and define h x as f x upon f dash x. Then this particular ratio, that is this new function that we have defined h x, has got a simple root at x is equal to xi. Therefore, this for this function x is equal to I is a simple root. What does this imply? This implies that since x is equal to xi is a simple root, I can now apply all the available methods that we have discussed for finding the simple root to find the simple root of h x is equal to 0, and hence the multiple root of f x is equal to 0, which is the multiplicity m. Let us try to get the first the Newton-Raphson method, the application of it to finding the multiple root. Now, what we are saying is that we are applying the Newton-Raphson method on h x. Therefore, the iterative method would be x k plus 1 is equal to x k minus h at x k divided by h prime at x k. Now, I need these two quantities to put here. So, I will have h at x k will be simply equal to f at x k divided by f prime at x k. So, that is from the definition of h x. Now, differentiate h prime. So, let us get out derivative of this, that will be d upon dx of upon f upon f dashed. So, let us differentiate it. So, if I differentiate, you will get f prime into f prime, that is f prime squared, minus f into f double prime divided by f prime whole squared. So, that is a simple derivative of f upon f prime. Therefore, I can now evaluate h prime at x is equal to x k and then substitute it over here. So, I can put this here and get it as x k plus 1 is equal to x k minus h at x k is, let us write f of k by f prime of k, that is our value of h at x k. In the denominator we have got h prime. So, this will go up as f prime k whole squared divided by f prime k whole squared minus f of k f k double prime, which we can simplify it in one more step, that is by cancelling f prime k one of them. So, I can write this as x k minus f evaluated at k f prime at k from here. The denominator is the same denominator, f prime k whole squared minus f k f second prime at k. Therefore, I can obtain the simple root of h x is equal to 0 using this Newton-Raphson method modification, and therefore, this gives me the multiple root of multiplicity of the original equation. Therefore, we can say that x is equal to x k finally approximation, this is xi, is an approximation to the multiple root. Therefore, we obtain the root without any further modifications in the Newton-Raphson method. Now, if this is always so, we do not need any other method, but if you look at the cost of the computation, the cost of computation is I need to evaluate f at k, f prime at k, f double prime at k. So, I need to, you can see this, we have got this f k, f prime k and f double prime k. So, I need to evaluate 3 evaluations to get the Newton-Raphson method, and the order of the method is same because we have evaluated the simple root of h x is equal to 0, the order of convergence is 2. So, the order of convergence is still remains as 2, and the only thing that we have done is one extra computation. If this extra computation is allowed and we do not have any problem, we can definitely use this particular method, but however, we shall give an alternative method to, so wherein we do not need evaluation of 3, we need evaluation of only 2, provided you know in advance the order of multiplicity. Now, this method can also be applied for secant method. We can apply the secant method. Let us see how you put in the same thing into the secant method. Now, in the secant method, let us take the way in which that we have written the computational way of writing the formula. We have written it as x k plus 1 is equal to x k minus 1 f at k minus x k f k at minus 1 divided by f k minus f k minus 1. This is the computational form of secant method that we have used earlier. So, therefore, I need to only insert into this what are the values of f k minus 1. This is equal to x at k minus 1 Now, I need to write this for the evaluation of the simple root for h x is equal to 0. So, I would now use the method as x k plus 1 is equal to x k minus 1 h evaluated at x k minus x k h evaluated at k minus 1 divided by h k minus h k minus 1. Now, we have written everything in terms of the function h x. So, let us substitute the value of what is h k, what is h k minus 1. So, that will simply give us x k minus 1 into f of k minus f prime of k, that is the numerator, minus x k, f k minus 1 is f k minus 1 upon f prime at k minus 1. Then the whole thing we shall divide by h k minus h k minus 1. So, f k minus f prime at k minus f k minus 1 f prime at k minus 1. Now, it is just a matter of simplification over here. We can see that from the denominator, first of all, we can write this as f k into f prime k minus 1 minus f k minus 1 f prime of k. So, I first simplified the denominator. When it goes to the numerator, we can see f prime k minus 1 cancels with f prime k f prime this. Therefore, I would not repeat that particular factor. So, the numerator would be simply x k minus 1 from here, f k from here, and f prime at k minus 1 minus x k f k minus 1 into f prime of k. So, that is the simplification of the numerator. So, this will be the secant formula as applied to Hx is equal to 0. Therefore, the order of the method is the same as 1.618, therefore, rate of convergence would not change. As we can see that we are in the secant method also we are now using f prime, whereas in the original secant method for finding f equal to root of fx is equal to 0, we have been using only fk minus 1. So, we have got only one evaluation at any particular stage, but here we need fk, we need f prime at k plus 1 and f prime k. Therefore, at any stage I need to evaluate two evaluations, that is your fk is required, f prime of k is also required. So, we have now again increased one function evaluation as the cost. Therefore, it will be more expensive than the normal secant method. As I said earlier, if evaluation of f prime k is not very costly, yes, we can definitely go about using this particular way of using the secant and the Newton-Raphson methods. However, if the multiplicity is known, let me assume that the multiplicity m is known, m is your multiplicity. Now, we would like to use the information, the definition of multiplicity as we have written earlier. Let us repeat it once more. The f of xi is equal to 0, f prime of xi is equal to 0 up to m minus 1th derivative, all of them are 0, and mth derivative at xi is not equal to 0. So, this is the definition of the multiplicity at of the root x is equal to xi. I would like to have a look at what happens the error analysis as we have done in the Newton-Raphson method. Let us start with the what is the definition of fk. Definition of fk is f of xk, and xk is the exact solution plus the error, the exact solution plus the error. Now, I would expand this in Taylor series. We are just following the steps that we have done for showing the error analysis of the Newton-Raphson method. When I expand it, I will use this information. Therefore, when I write f of xi, first term is 0, second term is epsilon k, f prime of xi, that is 0, and so on. All the terms, first m terms are 0 because of this information. The first non-vanishing term in the expansion is containing f of mth derivative of xi. Now, if I now write that one, the first non-vanishing term is epsilon k to the power of m divided by factorial m, mth derivative at xi, plus the next term is epsilon k m plus 1 by m plus 1 derivative f of m plus 1 of xi. Before I write the denominator, let us first simplify this expression, take out whatever is possible for us common factor here. So, I will take out the factor epsilon k to the power of m by factorial m, f m xi also I will take it out and write this as 1 plus what is I have taken out epsilon k to the power of m, I have epsilon k left out here, denominator m plus 1, and this ratio let us just call it as f. Let us call the ratio f as the ratio of f m plus 1 of xi divided by mth derivative with respect to xi. So, I have just taken the common factor here, and then I have written this remaining part as 1 plus epsilon k by m plus 1, f is this ratio, and whatever we have now writing here are going to leave the terms are of the second order terms and higher order terms. Now, the same thing we would like to do for the denominator also. Now, if I take the denominator will contain f prime of xk. So, this is f prime of xi plus epsilon k. is. Now I again expand this by Taylor series. Again I would be using the information that all these derivatives are 0 up to m minus 1th derivative, and this will be the non vanishing term. Therefore, the first non vanishing term will be containing f mth derivative, but this will be epsilon k to the power of m minus 1 by m minus 1 factorial and f of m xi, plus the next term is epsilon k to the power of m by factorial m f m plus 1 xi plus so on. Now, as we have done in the previous case, let us now take out the common factor here also, epsilon k to the power of m minus 1 by m minus 1 factorial f m of xi is again a common factor. So, whatever is left out is 1, epsilon k here, m here. This ratio is exactly the same, f m plus 1 divided by f m xi is the same as f, and order of epsilon k square. Now, I will take the ratio of f of x k upon f prime of x k. Now, let me just put this slide back once more. We have here f k is the factor outside is epsilon k to the power of m by factorial m f m of xi, and the factor here is epsilon k to the power of m minus 1 factorial mth derivative of h xi. Now, if I take the ratio of these two, you can see that f m xi cancels, epsilon k to the power of m minus 1 cancels, m minus 1 factorial cancels. So, whatever is left out is simply epsilon k in the numerator here, m in the denominator. So, remaining part gets cancelled out of this particular ratio, and what we have here is 1 plus I am writing this particular term epsilon k upon m plus 1 into f plus higher order terms. In the denominator I have this particular factor, which I will take it up and write this as epsilon k by m to the f this to the power of minus 1. So, I have taken the denominator up. Now, let us open it up or simplify it further. I will retain the first term as it is, epsilon k by m plus 1 of f, then I expand it out by binomial expansion, 1 minus epsilon k by m into f plus order of epsilon k square terms. Now, let us multiply it out and simplify it. So, what I will have here is epsilon k by m into 1, and epsilon k term is, this is 1 upon m plus 1 from here minus 1 upon m from here, epsilon k into f plus order of epsilon k square. This is epsilon k square, this is epsilon k square, this is epsilon k square. So, whatever is left out is all the terms, remaining terms of order of epsilon k square. Now, let us simplify it further. So, I would therefore have this as epsilon k by m into, now here I am simplifying this, therefore, I will have here m minus 1. So, I will have a 1 minus epsilon k by m into m plus 1 into f plus order of epsilon k square. So, this is what I have from the simplification. Maybe if you just want to have both the terms together, I will just bring this slide down once and we can just have a look at what we have this one. This is 1 minus epsilon k by m into m plus 1 into f this one. Now, let us put this into our Newton-Raphson method and see why the difficulty was arising. So, the method was x k plus 1 is equal to x k minus f k by f prime k. Therefore, we have the error as xi plus epsilon k plus 1 is xi plus epsilon k minus, now we have just now obtained the ratio this, and this is this ratio. Therefore, this is epsilon k by m into 1 minus epsilon k by m into m plus 1 into f plus order of epsilon k square. Now let us simplify. Xi cancels off from here. So the left hand side is epsilon k plus 1. The right hand side I will connect epsilon k from here. So 1 minus 1 by m into epsilon k. This is plus, we can write down what is this quantity, 1 upon m plus 1 f epsilon k squared plus order of epsilon k cubed. So we just collected the terms and written this as 1 minus 1 upon n into epsilon k. This is plus 1 upon m into m plus 1 f into epsilon k square plus so on. Now the error term has produced for the Newton-Raphson method this, the right hand side is epsilon k, therefore order is 1. Therefore Newton-Raphson method as applied to finding a multiple root would drop down the order by 1 from quadratic convergence to linear convergence only. As I said, this can easily be experienced when you are actually doing the computation. When you know that the method should converge fast after few iterations, what would happen in your computation when you see it, look at the results, you find that after even large number of iterations the error is only reducing it very slowly. And if you know the exact solution of the problem and then see the error is reducing by only a factor of 1 decimal place or so. Therefore this slow convergence will imply that you are possibly going at a multiple root. Now we have now shown that for a multiple root Newton-Raphson method has only order 1. Then what do? We can do a very simple modification to the Newton-Raphson method, and that simple modification is, suppose I start the Newton-Raphson method with xk plus 1 is equal to xk minus some alpha is a number constant, alpha is constant. So I would try to start a method like this. Now let us just go back to this slide once. What I have introduced alpha is, I have introduced an alpha for this, because this is ratio is fk by f prime k. So we have just evaluated the let me go 2 slides behind. We have taken the ratio of f by f prime k as this quantity, which we have finally brought it to the form of this as fk by f prime k. Now if I put an alpha over here, what I am doing here is I am bringing an alpha over here. If I am bringing an alpha over here, this is going to be an alpha here. That means this error expression would therefore look like, I would just write the same thing because straight away it is trivial quantity, 1 minus alpha by m epsilon k plus alpha m into m plus 1 f epsilon k square plus order of epsilon k cubed. Therefore if I introduce this alpha over here, I am introducing an alpha here in this bracket, 1 minus alpha by m, and I am multiplying here by alpha in this one. Now you can see that we started with alpha is a constant. If I now choose alpha is equal to m, then epsilon k vanishes. Now we shall say choose alpha is equal to m. If I choose alpha is equal to m, then epsilon k square is order of epsilon k square, or we can call it as c epsilon k square, where now c is this quantity alpha by m into m plus 1. If you open it out, what we had written it earlier, this is fm plus 1 xi by fm of xi. So the order has immediately gone up to 2, and now we have got the rate of convergence of this method is 2. That means again we have got back our quadratic convergence by simply using the order of multiplicity that is known to us in advance in the Newton-Raphson method here. If we are able to know it, therefore we are now avoiding evaluation of one more function. As we have seen earlier, we wanted evaluation of f at xk, f prime at xk and f double prime at xk for the Newton-Raphson method to have the required second order convergence. So, here I do not need any extra evaluation, I need the cost is the same, identically same as the cost as the method earlier method for simple root, except that we know in advance the order of multiplicity. So, that factor can be brought in here and then use that as the required Newton-Raphson method, the order of convergence would remain same. Of course, if you do not know the multiplicity of the root, we have to follow only the other way of getting the root. Now, let us take a simple example on this. Now, I take this equation x cubed plus 7 x squared plus 15 x plus 9 is equal to 0. I am giving the double that it has a double root, it has double root at x is equal to minus 3. Start the initial approximation x naught is equal to minus 2.5 and find the root corrected to 3 decimal places, and I would be using the Newton-Raphson method, the Newton-Raphson method that we have there. Now, the first thing is the multiplicity is given to us, it is a double root that is given to us, therefore, m is equal to 2 is given to us. Now, since m is equal to 2 is given to us, I would now write down my method as your xk plus 1 is equal to xk minus 2 times fk by f prime k. So, I would now be using that xk plus 1 is equal to xk minus 2 times fk upon f prime k. Now, let us substitute the values of f of xk, f prime xk, that is xk plus 1 is xk, 2 f of k is from here, that is xk cubed plus 7 times xk squared plus 15 times xk plus 9. We are differentiating with respect to x. So, I will have 3 x squared 3 xk square plus 14 xk plus 15. I have differentiated this is 3 x squared plus 14 xk plus 15 in the denominator. Now, we start the iteration starting with it is given to us the initial approximation as minus 2.5. So, I can substitute it here, k is equal to 0, I have the right hand side x 0, 2 times x 0 whole cubed, 7 times x 0 squared, 15 times x at 0 plus 9 divided by 3 x 0 square plus 14 x 0 plus 15. So, we just substitute the value of minus 2.5 in the expressions and then evaluate it from here. I substituted over, this is minus 2.5 and I evaluated the numerator 2 times minus 0.375, the denominator is minus 1.5 and that is equal to the value is minus 3.1. So, minus 2.5, the iteration has gone to minus 3.1. x2 will be, now I substitute x2 is equal to x1 minus 2 times everything evaluated at x1 numerator, denominator also evaluated at x1. So, I have here minus 3.1 minus 2 times I evaluated this at x1, that is at the value minus 3.1, I get minus 0.021 and the denominator is 0.43. I simplify the whole thing, I get minus 3.0023. Now, x3 I repeat the same thing with taking this as x2 and numerator evaluated at x2, denominator evaluated at x2. So, I have got here minus 3.0023 minus 2 times the numerator by denominator and this is minus 3.501. Now, we can see that in 3 iterations we have got an accuracy of 5 decimal places. Indeed, it would be very interesting for you to just take it as an exercise, solve the same problem by Newton-Raphson method without inserting this 2, without inserting the factor 2, you will be able to know just after 3 iterations with your computations that we are converging very slowly in this one. So, hence if of course, if I do not know the multiplicity that is given to us, I would go to the alternative way of finding the second derivative also and then using the Newton-Raphson method. Now, very important extension or application of the solution of a single nonlinear equation is a system of nonlinear equations. Why it is very important here is, if you in most of the practical applications, the mathematical model of the physical system is either ordinary differential equation or a partial differential equation, and in most cases the processes are nonlinear processes. Therefore, the differential equations that are produced are nonlinear ordinary differential equations or nonlinear partial differential equations. Now, we use some numerical methods, finite difference methods or finite element methods to solve these equations, and we produce a system of nonlinear algebraic equations which are the solutions at the, we call them nodal points, the points of intersection or the mesh. Therefore, what we have there is thousands of nonlinear algebraic equations, and the how do we solve it? It is possible for us to extend directly the methods that we have discussed now for solving the system of nonlinear equations. So, let us take the system of nonlinear equations as this. So, I have got n equations in unknowns. Now, as I said, it is not unusual to get few lakhs of equations, in particularly in finite methods, finite difference methods. If you have got a problem of 3-dimensional problem, in the 3-dimensional problem it is not difficult at all to get thousands or even few lakhs of equations, nonlinear equations. Now, one comment before we give the method is that we have already seen that if Newton-Raphson method is to converge, it is necessary to have some good initial approximation. We cannot be very far away from the exact solution of the problem. Now, the case becomes much more important, or discussion becomes more important in the case of system of nonlinear equations, wherein let us say you have got 10 variables, and if one variable or two variables you have given very accurately, but other variables you have given very far away from the exact solution, by the time those have been modified, the solutions which are close enough could be spoiled. Therefore, it is necessary that all these values through some other procedure or from physical considerations, one must have an idea of what could be the order of magnitude or what the type of solution that it could be, so that it can be used as your starting solution. We shall follow the same procedure as we have used in deriving the Newton-Raphson method earlier in one of our lectures. So, let us take the exact solution of this particular problem. Let us say the exact solution is xi 1, xi 2, xi n. So, this is the exact solution of this problem. We have used the Taylor series expansion to get the Newton-Raphson method. One of the ways of deriving, we have used the Taylor series method. We shall use that method to derive the method for the nonlinear equations. Now, let us take any initial approximation. Okay, x1 k, x2 k, so on xn k. So, this is any approximation. I would now add to this suitable quantities so that they become exact solution. That means, I will add xi 1 is equal to x1 k plus some h 1, xi 2 is equal to x2 k plus h 2, and so on. I will put xi n k plus h n is equal to xi n. So, I am adding the quantities, suitable quantities, so that I get the exact solution. Therefore, if I insert this here, I am xi 1, xi 2, xi n are the exact solutions. Therefore, when I substitute, it is satisfied identically. So, if I take the any equation ith equation, this will read as x1 k plus h 1, x2 k plus h 2 plus xn k plus hn is equal to 0. I have substituted these values in this. So, I is going from 1, 2, 3 n. What I now do here is I expand this in Taylor series function of n variables and retain only the first order terms. That means I would now write this as f I evaluated as x1 k, x2 k, xn k, plus look at this the expansion. This will be the h1 into partial derivative with respect to x1 evaluated at the point plus h2 partial derivative with respect to x2 evaluated at the point and so on. So, this will be having h1 into delta f upon delta x I by x1, will all of them evaluated at k. So, you can put it if you like at k. Then we will have this as h2 partial derivative of f I with respect to x2 evaluated at xk plus so on. We will have hn partial derivative of f I xn evaluated at k is equal to 0. Now, this I have a collection of these equations 1, 2, 3 n, all these equations. I take this is a quantity that is known to us, x1k, x2k, xnk is the iteration previous iteration. So, the computed values is all known to us. So, I can take this to the right hand side and then I will write this in the matrix format for each one of them. So, let us take I is equal to 1, 2, 3 so on. So, I will have delta f upon delta x1, delta f upon delta x2, f1, delta f1 by delta xn, f2 by delta x1, delta f2 by delta x2, delta xn. So, we are putting in the matrix format. So, this will be delta fn by delta x1, delta fn by delta x2, this is delta fn by delta xn, multiply this by h1, h2, hn. Now, I have written this particular thing, this is taken to the right hand side, therefore, I will have this as minus f1, f2, fn, all of them evaluated at the iterate k, kth iterate. This matrix, if you denote this by j, this by vector h, this is a matrix h, this is the right hand side, let us call it as f. F is evaluated at k, so I can put it f evaluated at k. This j is called the Jacobian matrix of the system. So, it has a name, it is called the Jacobian matrix of the system. Now, all these are also I can put a I think better we put a suffix here also, because delta fi by delta x1 all of them are evaluated at xk. So, this are all evaluated at xk, therefore, these are all numbers, these are all constants. Therefore, given at any iteration xk, we have a constant coefficient matrix multiplied by the vector and the right hand side is known. Therefore, what this has produced us is a system of linear algebraic equations. So, this is a system of linear algebraic equations. Now, therefore, we need methods for solving the system of linear algebraic equations, which is a topic which we shall be taking in the later lectures, how to solve a linear system of algebraic equations. Let us now consider a particular case of a 2 into 2 system and show how we can obtain the solution. We shall then apply it to get the solution in an example. Now let us take simply a 2 by 2 system and see how we can be able to solve a simple problem also. Let us take a 2 by 2 system, take the system as fxy0, gxy0. For this, what we will have here is delta f by delta x, delta f by delta y, and the second row is delta g by delta x, delta g by delta y. The vector is h1 h2, right hand side is fk gk. F is evaluated at xk yk and g is evaluated at xk yk. And what will be the next approximation? We should have mentioned it there. The next approximation will be, as you can see, x1k plus 1 is equal to x1k plus h1, x2k plus 1 is x2k plus h2, xnk plus 1 is xnk plus hn. So the remaining part is the same as the Newton's method. So this is really an extension of Newton's method to a system of nonlinear equations. So when once we determine this h1 and h2 from here, we can go back, evaluate this partial derivatives again with respect to k. I can as well put this as a suffix with k. I will evaluate everything at the current iterate, again solve the system, get the increment, then again repeat the same thing. So that means for each iteration we shall be solving one linear algebraic system of equations. The order of the system depending on the number of equations that is given to us. Here we are solving 2 by 2 system. In the general case we are solving n by n linear algebraic system, one particular system for each iteration. Now let us take a simple example on this. The problem is given is that we are given the x square plus y square is 1.12. I have taken a simple example in which you will be able to eliminate it, but we will not eliminate it. Just to illustrate it, a simple example, x square plus y square is 1.12, xy is 0.23. The solution of this problem is close to 1 and 0.2. So that means we are given initial approximation to the problem. Find the solution after one iteration of the Newton's method. So what I need to build up is the Jacobian matrix of this first. So I build up the Jacobian. Now we will write this as fxy as the first equation. So we take everything to the left hand side. You remember we are writing this, we will have to write this as f1 of xy is equal to 0, or f and g we are writing, f g of xy is equal to 0. So these are the two equations. Therefore I will bring this right hand side to the left hand side and define it as f. For the second equation I bring 0.23 to the left hand side, define it as gxy. Therefore fxy will be x square plus y square minus 1.2 and gxy is equal to xy minus 0.23. Then the Jacobian matrix will be differentiate this partially with respect to x, differentiate this partially with respect to y, then differentiate g also partially with respect to x and y. So I have here 2x, I have here 2y, and the derivative of this will be y and x. Therefore the Jacobian matrix is this. Now since it is a 2 by 2 system, what I have done here is I have inverted it, because then when once I invert it I do not have to repeat the solution of system of linear equations. I just have to evaluate what it is. So it is a 2 by 2 system, so I will find the determinant of this, that is 2x squared minus 2y squared, that goes into the denominator. I will write down the cofactors for this. Cofactor for this is x, cofactor for this is 2x, cofactor for this the cofactor, and its we take the transpose also. So I take minus 2y minus y here. So I get this as the inverse of this particular matrix J. When once I write this as the inverse of the matrix, I can now write down my system of equations. So h1 h2. Now what we are writing here is, next step is that we are writing this vector h is equal to j inverse of fk. So this is h is equal to minus j inverse of f at k. Now we have h is equal to h1 h2. We have just evaluated the j inverse. So I substitute it here, 1 upon 2 x minus x square minus y square, and the Jacobian is this that we have just now written it. Now I will substitute the initial values, x0 is 1, y0 is equal to 2. Then it is simple matter of computation. So this is 1 divided by 2 times I have computed what is x square minus y square, set the value of x as 1, 2x is equal to 2, minus 2y minus 0.4, minus y is minus 0.2. Now this is the evaluation of f at xk, f at xk yk, that means I have evaluated, I will just put it here, I have just evaluated fxy and gxy from this and written these values as minus 0.08 and minus 0.03. Now just multiply it out and divide it out by this quantity and produce this as 0.0354, 0.029, and we have x1 is equal to x0 plus h1, y1 is equal to 0.2, that is your initial approximation given to us, plus 0.0229, that is 0.2229. This is the solution of this particular problem. The initial approximation was given to us as 1 and 0.2, and now we have got the new solution as 1.0354 and this. Now it is possible for us to check the error in satisfying the given equation, that means we can just put these values in the equation and see whether f is sufficiently close to 0 or g is sufficiently close to 0, and the values are f at x1 y1 is equal to x1 square y1 square minus 1.2 00174, and g x1 y1 is this. So it is, when we have started it initially, the values of f and k were here, this is your f at xk yk, g at xk yk. The what the value minus 0.08 is now reduced to 00174, and 0.03 has reduced to 3079. So that means the how we are talking of how the whether the equation, because one way of testing it is whether how the equation is satisfied. So we are now testing whether the equation has been satisfied sufficiently. Now we are able to get the accuracy faster. It probably you need just another 3-4 iterations to get an accuracy of 4-5 decimal places. Therefore it is possible for us to solve a system of nonlinear algebraic equation also by simple extension of the Newton's method. Now earlier we made a comment that of all the method that is available, that the Newton-Raphson method is the most commonly used even today for any scientific and engineering applications. The reason we have given was the reasonable order of the method and the computational cost. Now if you look at this nonlinear system, you will find that the extension of secant and other methods will be much more complicated, much more difficult, and therefore the Newton-Raphson method is very valuable for the system of nonlinear equations also. We have all along talked of the real roots, a simple root, multiple root. Now how do you get the complex root? Because if an equation, if you say you want to solve x square plus 1 is 0, so it has no real root, so they are all complex roots. How do you get the complex roots? All the methods we have done, all of them work, except you have to do complex arithmetic. You have to start with the complex approximation, initial approximation, and do the complex arithmetic. Every method that has been done so far can be used. Therefore that is what we have. For example, I can write down the Newton-Raphson method as zk plus 1 is equal to zk minus f of zk by f prime at zk, k is equal to 0, 1, 2 and so on. Now the only thing is, a real approximation cannot lead to the complex. So I need to have the complex initial approximation and I do the complex arithmetic. So you can define in advance your the computation as complex and then go start with the initial approximation and perform it, and the order of convergence retain the same whether it is a real root or complex root, there is no difference. Therefore we do not need any special method for obtaining the complex roots. However, we can derive an alternative method for solution. We shall illustrate this method through an example. Let fz is equal to z square plus z plus 1 is equal to 0 be the given equation. Set z is equal to x plus iy. Then we get f of z is equal to x plus iy whole squared plus x plus iy plus 1 is equal to x squared minus y square plus x plus 1 plus I into 2xy plus y is equal to 0. Now setting the real part 0 and the imaginary part to 0, we get the two equations, x squared minus y squared plus x plus 1 is equal to 0, 2xy plus y is equal to 0. This gives a system of two nonlinear equations in two variables x and y. We solve this system by the Newton's method that we have derived earlier. However, in this case the computation may take more time. We shall choose this procedure if we cannot perform the complex arithmetic and using complex initial approximation. Therefore, the general technique in this particular case would be that substitute z is equal to x plus I y in f z is equal to 0, separate the real and imaginary parts, put them equal to 0, solve them as a system of two simultaneous nonlinear equations in two variables x and y. That gives the alternate method of the method Newton's method that we have discussed earlier. We shall stop it for today.